Hi, my name is Joe Diederich, and the title of this presentation is a classification system for rule extraction from support vector machines. First of all, I'd like to say thank you to the conference organizers, in particular Dario, for making this quite unusual presentation possible. I really appreciate it. Thank you very much, and I hope you find it interesting. This presentation is about rule extraction from support vector machines, and it gives me a chance to introduce to you a new classification system, new evaluation criteria for rule extraction from support vector machines, which I think is necessary for the current research. This is essentially the takeaway message of this presentation. There's a lot of work now on rule extraction from support vector machines, and in the context of this work, evaluation criteria that originally have been developed for rule extraction from neural networks are applied. I believe this is problematic in a number of ways, but the most important point is that support vector machines have been designed for high-dimensional input. Hence, we have to design rule extraction algorithms that allow us to extract meaningful, semantically comprehensible rules from high-dimensional datasets. In the later part of this talk, I'd like to give you one example where this is possible, but prior to that, I would like to outline the issues that are important here. I'd like to present you this new and refined classification system for rule extraction from support vector machines, and then go on and present one new system to you, which my colleagues and I are working on right now, which is called SVM, which allows to extract propositional rules from support vector machines. The advantage of this system is that only support vector machines are used, even for the extraction phase, but of course there are disadvantages as well, for instance, low fidelity. Now, why are we working on rule extraction from neural networks to begin with? Well, as everybody knows, neural networks are now applied for decades in a number of different fields because they have a number of interesting and good features. This includes online learning. I can simply retrain a neural network by adding new examples. I don't have to use the entire dataset if I wish. And of course, neural networks, feed-forward neural networks, easily can do multiple classification, regression, and similar tasks. I believe this is one of the major reasons why neural networks are still of interest and are being used right now for text classification, in particular in those cases where we have a very large number of outputs, as we obviously can have in the context of search engine technology. Now, applying neural networks comes at a price. When I'm using a feed-forward perceptron and multi-layer neural networks, I do not know how a certain result was achieved when I get my classification from the neural networks. So I have to apply additional techniques like rule extraction from neural networks to get a comprehensible rule set that hopefully explains how the neural network arrives at a certain decision and why a certain output was obtained. This is obviously in contrast to methods in artificial intelligence, where you have a symbolic and declarative knowledge representation. Now, this is well suited for explanation, and work over the last decades in AI has led to explanation systems that actually distinguish between the AI system that is being used for classification on the one side and the explanation component. Rule extraction from artificial neural networks then serves a dual purpose. Number one, to explain the result of a classification task, for instance, as obtained from the neural network, to explain this result to a user, but also to explain how the neural network has arrived at a certain decision. Now, these are two different objectives, obviously, and sometimes they're in conflict, both in the context of rule extraction from neural networks as well as rule extraction from support vector machines. About 10 years ago, my colleagues and I worked on a classification system for rule extraction from neural networks. And interestingly, this classification system is still in use, and it's being applied now for rule extraction from support vector machines. The original classification system, as applied to neural networks, had a number of different dimensions. The first one is the translucency dimension, and here we're typically distinguishing between decompositional components, or rather decompositional algorithms, that are taking components of the artificial neural network, like hidden units, and turn them into rules. Later, I would combine all the rules to a rule set and potentially refine the rule set. Also, I have learning-based approaches that, in a sense, are learning what the neural network has learned, and sometimes these methods are called pedagogical approaches. The second dimension is the expressive power of the target language, the rules being extracted from the neural network, and this can be anywhere between Boolean propositional rules, fuzzy logic, or in some cases people have tried to extract first-order logic rules from artificial neural networks. The third dimension is a portability across artificial neural network architectures. Some of the algorithms, in particular the decompositional approaches, only work for given artificial neural network architectures, while other, in particular the learning-based approaches, are portable over a range of ANN architectures. The quality of the extracted rules is very important, and there are a number of criteria which are important, and they're now consistently applied, actually over the last 20 years or so, because Towle and Shaflik in the late 80s introduced criteria for rule quality, and we're still using them and developing them in the context of rule extraction from neural networks as well as support vector machines. A few words on this later. And also the complexity of the rule extraction algorithm, which can be high, in particular in case of multi-layer feed-forward neural networks, those with at least one layer of hidden units. I've mentioned rule quality and the criteria for rule quality, which are really important, and I think it is sort of a healthy sign of or a healthy sign for the whole scientific community working on these issues, that there's an agreement on these rule quality criteria. The first one is accuracy, and this is the extent to which the rule set, independent of the originating neural network, is accurately classifying new unseen patterns. So it's a generalization capability of the rule set independent of the neural network. The second criterion is called fidelity, and this is a question: to what extent is the rule set mimicking the underlying neural network? Is the generalization behavior of the neural network actually identical to the neural network, to the generalization behavior of the rule set? Again, sometimes accuracy and fidelity can be in conflict, but fidelity measures the level of agreement for unseen examples between the rule set that has been extracted and the artificial neural network. The next evaluation criterion is comprehensibility. Now, this is actually a numeric measurement, and it has two parts. And next I have consistency. And here I'm addressing the question of a number of runs of the rule extraction algorithm. Given a certain data set and a certain neural networks, do I always get the same rule set? Or due to the effect of initial parameters, can I get different rule sets for different runs over a given neural network and a given data set? And again, there are some rule extraction from neural network algorithms that allow consistency, others not. Let's focus on the first dimension, which is the translucency dimension. And here I have decompositional approaches which allow me to open up the neural network to look at individual components like hidden units and output units, to decompile essentially hidden and output units to arrive at rules which are then later combined. And on the other side, I have pedagogical approaches which are treating the neural network as a black box, and these approaches are trying to learn what the neural network has learned. So let's look at the decompositional approaches first. We are extracting rules at the level of individual hidden and output units first, and we do this one by one. Sometimes it requires an intervention into the neural networks by changing the output function of hidden units and sometimes output units as well, from, say, a sigmoidal function to a simple step function. This is because we want to have Boolean rules with 0, 1 output. And after changing the output function of the hidden unit, we would test if the classification and generalization behavior of the neural network is still acceptable. Once I've done that, the task then is to search for incoming links to hidden and output units. As a matter of fact, groups of incoming links to hidden and output units, which for any combination of inputs allow an activation of the hidden and output units independent of the activation that is present over other input lines. So I'm taking individual hidden and output units. For the set of weights, I'm searching for a combination of weights that would activate the hidden or output unit independent of the activation that may be present over other incoming links. I would do this for every hidden and output unit, later on combine the rules to a concise rule set, and potentially use algorithmic techniques to refine and to minimize the rule set. Pedagogical approaches, which are treating the underlying artificial neural network as a black box. Typically, this is being done in conjunction with conventional or symbolic machine learning techniques, such as a decision tree learner. We will have an example of that in a moment. And of course, I can have possible combinations of decompositional and learning-based or pedagogical approaches. This here is the learning-based rule extraction algorithm that has been proposed by Craven and Shaflik now 12 years ago, which is a little bit the mother of all rule extraction algorithms that are learning-based. And this is a simple algorithm based on pack learning, which essentially has two oracles, one that is simply producing individual patterns, the example oracle, and the other one is the classification oracle, including subset. Now, what's happening here is that simple rules are being formed by taking individual examples, turning them into rules, and these rules are then being generalized. We have a loop through the antecedents of individual examples now turned into rules. Antecedents are dropped one by one. This is the generalization step. And then the subset algorithm for a given output class and a given modified rule, here R prime, would check whether there's still agreement between a given rule, modified rule, and the classification of the neural network. Now, it has been shown by a number of researchers, including a former colleague of mine, Mostafa Golea, that subset, even in the context of this rule extraction algorithm, is NP-complete. So it is a complex process, and people have introduced heuristics in order to improve the efficiency of this algorithm. Now, let's talk a little bit about support vector machines. Support vector machines are, in a sense, dominating or have dominated much of machine learning for about 10 years now, because they have a number of properties which are clearly desirable. They have a very, very good and sound theoretical foundation. They are a result of efforts in computational learning theory. The objective is to find the low truest error after learning has been completed. The support vector machine tries to find the minimal error, the minimal true error after completion of the learning process. And by way of built-in regularization, overfitting is being avoided. So as a result of this, clearly support vector machines have a number of advantages which are balanced by disadvantages as well. We're going to talk about this in a moment. I'm sure most of you have seen this particular figure in this demonstration, which is probably the most overused and classic one when it comes to support vector machines. I'm trying to find a boundary that is separating patterns that belong to a target class and an alternative class. We have a binary decision problem here. I'm trying to position the hyperplane that, in an optimal way, provides the classification. The support vector machine as a maximum margin classifier would aim at maximizing the margin between those training examples that are close to the decision boundary, now called support vectors. Now, by doing this over essentially a number of support vectors, maximizing the margin, I'm positioning the hyperplane in an optimal fashion, and this essentially results in good generalization. Obviously, I can have misclassifications, and I can have examples on the other side of the boundary, and there are ways to deal with that. Support vector machines have advantages and disadvantages. The clear advantage is that they can take high-dimensional inputs. The classic application for support vector machines is probably text classification, as introduced almost 10 years ago by Thorsten Joachims, where in a text classification task I have very high-dimensional, sparse input patterns. In particular, if I have a so-called bag of words representation, I'm taking individual words as features, I'm counting the frequency of occurrence of these words in a document. These are then values of my attributes. I may normalize this or take some other, have some other pre-processing steps. But if I have a very, very simple bag of word representation in text classification, just taking individual words and count the frequency of occurrence, in many text classification tasks, including authorship identification, I can have very, very good results. So the capacity to accept high-dimensional sparse input clearly is an advantage for application areas such as text processing and image classification, among others. But there are disadvantages as well. For instance, there's no online learning. I cannot add examples and retrain the support vector machines as I like. I have to train and optimize an entire data set. Learning can be slow. For certain data sets, particularly in text classification, if I take volumes of a newspaper, for instance, it's an issue. And I think in a number of application areas, certainly in projects that I have done with colleagues, support vector machines have not really shown any advantage for data sets that are low-dimensional. So if you have low-dimensional data sets, you may want to use and try a decision tree learner, which can also give you very, very good results. I think the main advantage of support vector machines really comes through when you're using high-dimensional sparse inputs, hence an issue for rule extraction from support vector machines. Over a number of years now, a number of research groups around the planet have published work on rule extraction from support vector machines. And interestingly here, we can again distinguish between decompositional approaches that at least in part are taking the support vectors as input and using them for the formation of the rules, and those approaches which are learning-based, which means they are using the support vector machine as a black box and use another learning-based approach to extract rules from the support vector machine. So at first sight, the decompositional pedagogical dimension works. I can talk about translucency, and many people are doing this. Also, in current work, people are using the same rule quality criteria as has been used for rule extraction from neural networks. And again, this can be a little bit problematic, as I'm trying to point out in a moment. What is really troubling is that most of the experimental results that have been published are on low-dimensional data set. I've just recently seen a paper where people introduced a new rule extraction from support vector machine technique, and the first data set they've used is XOR. Now, that's not what support vector machines are designed to do. Support vector machines, again, demonstrate their clear advantage for sparse high-dimensional input patterns. So we have to develop rule extraction from support vector machines that are working for sparse high-dimensional input patterns. To my knowledge, and I would like to learn about this more, but to my knowledge, at this point in time, there is no rule extraction from support vector machine technique out there that is really generating concise, good rule sets for data sets that are high-dimensional. Just by way of overview, as I said before, there are a number of decompositional and learning-based approaches out there. Nunes and co-worker in 2002-2003 have introduced a method that can be classified as decompositional, even slightly inaccurately so. It is using clustering techniques to define prototype vectors in the dataset, and is then combining these prototype vectors with support vectors in order to arrive at rules. And there's Zhang et al., who published last year in 2005 a method that is generating hyperrectangles in input space, starting with small regions, which are then incrementally enlarged, and later this is being mapped to rules. There are also learning-based approaches, and one of my former co-workers, Nakhla Barakat, and I, we've published on this, including several papers in 2005.